So my name is Răcănel, and together with my colleague Ionuţ-Radu, we try to show you, let's say, not a new method, but another way to consider the estimation, the capacity strength of existing road bridges in Romania. And let's say the idea of the study emerged several years ago, when in discussions with our colleagues in the design companies, the starting point of the whole discussions was how we manage with the old bridges designed with previous norms in Romania. And the discussion started because since the 1st of July 2010, it was the Euro norms were introduced in Romania. And most of the ideas were that what we have to do with the existing bridges, probably most of them should be demolished and replaced. And in discussions between us, we said, let's try to see if we find a way to see if it is like this. And so this was the idea of this approach. This is the content. So a short introduction, then a description of the method.
Dar nu putem sta fără lumină în sală. Așa adormim. Chiar că adormim. Cum vă este mai bine? Fără lumină sau cu? Ok. Rămânem cu lumină.
Să stingă numai pe cea de la scenă.
Păi este stinsă cea de la scenă.
Să reflectă acestea de aici, să reflectă de ăsta.
Că stă tremură tot.
So we will show you some results on some bridges we analyzed, and then roughly the conclusions. I resume here the main causes leading to strengthening of or repairing of a structure. And this necessity comes from, of course, when it comes from the gradual changes in weight and geometry of the vehicles. Maybe from the natural damaging, and I include here all the events, including earthquakes and floods and other natural calamities. Of course, the changing in the design standards, I already spoken about that. Accidents, I can include what's happening in Lucca in the category of accidents, because there was an artificial cause leading to the collapse. Maybe the current needs for reorganizing the traffic in some areas, and in the light of the actually geopolitical, let's say, status, the political other military reasons, especially for the bridges placed near borders. The capacity of a bridge, resuming simply, depends on the efficiency and functionality of the adopted solution, because there are many ways to retrofit or replace a bridge. The characteristic of the physical characteristic of the materials, the correct estimation of the future traffic in the area. Of course, depends on the performing the current maintenance, because here in Romania, it's a problem with the maintenance. We have a problem with the maintenance. Mostly when we finish a bridge, most of the constructor or the administrative persons think that's all. Starting from now on, the bridge is there and nobody cares. It's not a good approach. And related with the maintenance work, the long-time monitoring, which is another, in my opinion, and for the new bridges where I took part for the design, I try to introduce all the time, especially for new solution or important solution, the long-time monitoring. Long-time monitoring is not a monitoring on half a year. this is neither way long-time monitoring. Long-time monitoring should be continuously made on the service life of the bridge. Who takes the decisions to establish the need of strengthening or retrofitting? And the decision should be taken by the authorities, administrative authorities, together with the designers and other involved factors, but should be based on the following factor or following conditions. Correctly estimating the severity level of the damages. This because, as the colleagues from Japan showed us before, in the first stage it's only a visual constatation of the damages. It should be right interpreted, the severity level. The second component is to calculate, but implementing the damages or taking into account the level of the damages. It's very difficult to make because of all the models that are used in the calculation should physically modeling the damages. And we know all that there are an infinity of parameters to take into account. It's very difficult to mathematically model the damages. And the third component, but not the last one as importance, is the testing and checking the performance of the performance of the materials. Almost in all cases, the decision is taken by seeing visually the structure and then make some calculation according to the related standards available in the moment of the inspection. And starting from this assumption, we try another approach. The approach is based on, let's say, appreciation or estimating the vulnerability of the bridge in terms of resistance capacity. And we try to find out the law of distribution of some parameters involved into the capacity of a bridge in order to establish some percentages of overpassing these values. And we started with bending moments, resistant bending moments, and with the vertical displacements, because they are the most simple parameters to take into account in order to estimate the capacity. The method is based on the following assumptions. So, in terms of permanent loads, in the new norms, in Euro codes, there are very small differences for estimating the permanent action acting on the bridge. The main differences come from the traffic, which are quite different in the Euro codes comparing with the old Romanian norms. The second hypothesis is we should have sufficient data for the traffic, because in a discussion several years ago with another administration company, when I asked for this kind of data, they told me we have it, but they don't have it at all. They have the data according to the type of vehicles, for example, trucks, automobiles, small vehicles, but they don't have data concerning the number of axles, the distance between axles, longitudinal, transversally, this is very important, the number of vehicles, and the evolution of traffic. We don't have such kind of data, so far as I know. The traffic data, mostly they are available by measurements. When I was a student, we made this kind of measurements here in the near. Okay, they were not so many vehicles as at the moment in Bucharest, but we usually, as students, we made some some traffic measurements. So the method we proposed was first introduced by Vambatsikos and Danan for estimating the vulnerability of bridges for the size of structures for the seismic action. And we try to adapt this method, and we check how we can adapt this method for estimating the strength capacity of bridges. So as I said before, as parameters for the study, we chosen the bending moments in the middle of the span. And you will see that the structure is not so complicated. We try to see if the method works. And the vertical displacement coming from the traffic only. So we didn't take into account the vertical displacement of the bridge coming from the permanent action, because more or less we assume that there are no variation. It is not strongly dependent on the norm. So the target was to establish a distribution law and determine the probability density cumulative distribution function to be considered for the chosen set of values. Here is some, you already know the mathematics describing this approach. We chosen a typical bridge in Romania. The beams are simply supported. You can see they are 4 precast concrete beam. The span was around, we analyzed many bridges with several set of spans, but this one had around 30 meters. Before to start the analysis, we imposed, or we thought a method to strengthening the bridge, and the chosen method, the most appropriate chosen method, seems to be to add a supplementary concrete slab. And starting from this assumption, we check if it is like this for several different thickness of the concrete slab. We started with 10 centimeters for the new concrete slab, 15 and 25 centimeters of the concrete for the thickness of the concrete slab. So that means for the whole bridge, the concrete slab was removed, the way layers, the footways, the bridge was enlarged to accept new width for the roadway, then also a larger cantilevers for the footways. So on the left you see the cross section of the existing bridge, and on the right you see the cross section for the retrofitted bridge. So we started analyzing the bridge for all these assumptions, for all these separately adopted solutions. The analysis model is not so complicated, it's a simple one. Could be, we used here the grillage for the beams and the plane stress, four node plane elements for the concrete slab. It's not important. Could be made by using any kind of finite element model. The problem was to achieve the possibility to have a good probabilistic approach, because in order to have one, we need at least 51 group of values, minimum. And there are not so many vehicles in the norms to cover this aspect. And then we made our own grouping of vehicles and place it on the superstructure in order to achieve this goal. You can see here this kind of vehicles. They are present in the all norms, in Eurocode also, but also in the are some group of vehicles which are used for testing in situ the bridges in Romania. So after finalizing the execution, then we use some position of the vehicles, measuring some data. So we combine all these kind of vehicles in order to have sufficient data in order to apply and to obtain a correct distribution law. So instead to have the comparison, as I said before, at the level of the bending moments, we try to refine this analysis by using as parameter the normal stresses and the bottom fiber of the beam, of the most stress beam, which was the lateral, the edge beam, one of the edge beam. We established the reference values, as you can see there, because we took into account the value indicated in the norm, so 3.2 megapascal tensile stress, as have this as a reference for the stresses. And the other parameter was the vertical displacement of the most stress beam, also in the middle of the span. So the limit value for the displacement was taken from a normative existing in Romania. This is PD 165 from 2000, and there the indicated value was the span over 800, and it resulted almost 37 millimeters as a limit displacement. Then running the analysis and made some histograms. You can see here the distribution fitted on intervals in this slide for stresses, for normal stress. As I said, at the bottom part of the edge beam. These are the cases without retrofitting. This is on the left corner up, and then with all the stages considered as solutions for retrofitting, 10, 15, and 25 centimeters. These are the probability density functions. And according to this, we established the cumulative distribution functions, which are these. And from all this, we thought we can use a normal distribution, which fitted well on this, according to this obtained results. And following the analysis we perform, you can see in the tables above the values for the stresses in all 4 stages on the left, and the frequency of the normal stress in the bottom fiber over intervals, and on the right side you can see the displacement values also in all 4 cases, analyzed cases. So if you take a look on this, especially in the normal stresses, you can see that most of the values are in the range -3 to megapascals, which is good for all the solutions we try to adopt. So we are okay. We are below 3.2. Continuing the study, we established the probability density functions for the normal stresses and for the displacement. And based on this, we could establish the reliability functions. And from this point of view, shortening the presentation, at the beginning, when we suggest as a retrofitting solution adopting a thicker concrete slab, we thought maybe around 20-25 centimeters of a new concrete slab will improve a lot the behavior of the bridge. And we had a surprise analyzing the reliability curves. We could see that the most efficient solution is the one with 10 centimeters new concrete slab. And we thought, how can be this real? having a thinner concrete slab better than we have a thicker one. And analyzing the results, we conclude that this appears to be to introduce a balance between the permanent and live loads. So further on, increasing the thickness of the slab, of course, we can decrease the efficiency of the bridge because we take from the live loads. So in this manner, we can establish for this kind of structure, but the method can be applied for other or any other structure, which is the more reliable solution in terms of, let's say, for example, stresses, normal stresses, tensile stresses, or vertical displacement. From the point of view of the displacements, the structure behaves well. So for this kind of bridges, we didn't have some problems as, let's say, cracks or severe deformations. So we didn't met this kind of problems. In terms of stresses, of course, we have had. So I don't pass to the conclusion because I already presented you most of them during the presentation. Thank you very much.